And today I'll talk a little bit about the work that we've been doing in my lab for the past 2 years. So specifically, I will focus on mechanics, right? How do forces, displacement affect some of the systems that we study, particularly in the human body, but then also electromagnetics, right? When we have electric fields, magnetic fields acting both in the body, but also in technologies that we put around it, on it, or in it, right? So we care about forces, we care about electric fields, we care about materials, and how those come together to integrate in technologies that we put into the body. So we want to engineer as a verb, mechanical systems that adapt to the body in its mechanical elasticity. They're soft, they're curvilinear, or also they can vanish completely through natural biological processes. So we can envision stretchable devices. They can manipulate, bend, twist, stretch, but they also have an electromagnetic functionality. So you're not compromising between the ability to bend and conform some patch to your arms, and the ability to transmit, send, receive information. And on another exciting sort of axis of that technological spectrum, we have devices that are engineered with the purpose of disappearing, right? So you have chemical processes that are actively degrading the device, so you need to really model how those timescales of functionality, but also timescales of degradation occur, because you have functional elements acting at different states, right? So you want to send information, but you cannot do it all the time because your device is disappearing. So for the purpose of this talk, I'll focus only on 2 examples of some of the most recent work, one of them in soft materials, and then some of them in hard materials related to the body specifically. So a very exciting thing that we proposed recently was a wearable system that is able to track the amount of milk that is leaving the breast continuously over a breastfeeding session, to be able to link electrical signals to be able to link milk information to an electrical signal reading, to be able to correlate the amount of milk leaving the breast and the amount of signal that you're sensing. So this is particularly important when you have neonatal patients or other fragile sort of patients that are breastfeeding, and you really want to have a quantitative metric of the amount of milk that the baby is receiving. So we engineered this system that acts as a bioimpedance device, where the idea is you're going to deploy this in a space with huge variability, right? You have the geometric and volumetric parameters that come from the breast, and then you have tissue properties, right? You have skin, you have fat, you have globules, you have milk, all of them that are spatially varying between your specific patient, and then you want to be able to link a bioimpedance response to what's happening when the milk leaves the breast. So we're able to reconstruct anatomical scans and then run these bioimpedance simulations to be able to quantitatively link amount of milk with a bioimpedance response, and then be able to say, okay, the neonatal patient is ingesting this amount of milk over a specific breastfeeding session. So how does the modeling strategy work? We have a bioimpedance system, so we're basically sending a small amount of current through one of our top electrodes, I1, and then we have a ground electrode at the bottom of the breast. So we have sort of this volumetric coverage, and everything in between, we have these tissues spatially distributed, so we can sense when there's the presence of milk and when the milk is leaving as a function of time. So in that way, we can plot it as a function of frequency, and we have 2 curves, the one when the breast is full and then the one where the breast is empty. So that delta can be maximized from simulations to tell you where you need to place your electrodes and how much of that change is due to milk only. So then you get to start to ask a bunch of super interesting questions in terms of electrode placements, how many electrodes you get, and then as you start to go into a little bit more clinical questions that might be relevant for people in this field of nutritional content of milk, what is happening with the quality of the milk? So essentially, we're trying to link AC currents to an impedance reading that is affected by dielectric and tissue changes. So that will give us a metric of milk outflow. So from a brain phantom perspective, let me see here if it transitions. Okay, there you go. So we want to validate this sensor, right? We want to validate this metric, so we come up with some experimental measurement here where we have a very simple semi-hemispherical tissue phantom. We put milk, and then we track from the simulations those internal changes on the structure and the way that the electrical current density, the electric field density is going to vary when you have different volumes of milk. So here it's kind of like a simple benchtop validation before we go all the way to specific reconstructions from every patient. And we can see that the change in impedance, the C term that comes from our sensing electrodes, is a function of the real and imaginary part of the sensing 2 and 3 electrodes. So we can link in a linear plot the experimental data and the simulation data without fitting. We're not sort of like adjusting by a scale. We're just saying that this change is due to a dielectric shift internally on the breast. So that allows us to then track on a breastfeeding session. So we're looking at time versus change in impedance, the fluctuations in impedance as the milk is leaving the breast. So then we can collapse those measurements into a single master curve that is plotted here as change in impedance over milk output volume. So this is a linear scale. And the trick here is the following. We have two parameters. If you look at the Y scale, we have impedance change, which happens because the milk is leaving the breast. So you have essentially a dielectric shift in your system, normalized by the initial impedance. Now, this initial impedance carries patient characteristics, shapes, volume, milk distribution. So all of them, when you normalize them by this patient-specific parameter, you can collapse them into this linear relationship. So that way you can say, for expressing 100 milliliters of milk, you can have about a 10%, 15% change in impedance from your sensor. And the key here is that we're dealing with a fluid that we don't see, right? So we're trying to link those characteristics from the milk outflow and then what the baby ingests. So we have a way to sort of like link that internal, those internal metrics through a wearable system that just plays conformally around the skin. Now, that was in the soft materials part. Then let's move into the hard materials part with bone. So this is another collaboration that we have here with clinicians at MD Anderson, and we're looking at digital reconstructions of spinopelvic osteosarcomas. And the idea is, can we provide some sort of quantitative guidance from a mechanical perspective to which bones we can select to do this reconstruction? Because what currently happens is with spinopelvic osteosarcomas is that the surgeon goes in and then they resect different sections of the pelvis and then they have to stabilize it. So if you're in the structural mechanics side, engineering side, you're really looking at, okay, the stability of my structure, will this structure fail? So it's the same kind of framework that we use for bridges and sort of like these large scale structures to the body, right? Because essentially we have trusses, we have systems, we have force transmissions, and we have stresses and strains that develop because we have effectively a composite system here. But now it's bone, cortical bone, cancellous bone, and the implants. So here, when we are faced with the choice of, okay, which one would you want, right? If you're a patient, how do we engineer this to be able to hold structurally all those elements that come into play? Then we go and run some structural analysis simulations. So the key thing to note here is that the one in the left, that's the post-op tibia reconstruction. So that's actually what happened to the patient, and the other ones are digital reconstructions. So we're able to mirror the actual clinical case with digital reconstructions of what we would predict would happen if we use different bones. And the idea here is that you have the X-ray scan, and we go from something that has, the healthy pelvis, the reconstruction, and you have different parameters that you can play with, not just the bone graft, but the angle of the bone, right? The length of that spacing, and then also the number of screws that you have to put in to secure different locations of your spine of the remaining pelvis. So this way we can quantify those surgical choices that are sometimes made, from physical intuition and where to put their screws with some sort of quantitative metrics that tells us, okay, this is the best choice for this particular patient. So that kind of like level of individualized medicine. And our reconstructions follows the same, this pipeline. We get the clinical imaging, CT scans, X-rays from the clinical teams. Then we go and reconstruct and clean up these files so that they're able to be run using finite element simulations where we can virtually assign sort of those loads and predict those sort of characteristics that will come after different kinds of loading conditions. So sitting or some other postural changes. So in that way, we can isolate the effect of both bone choices, but also specific implants, right? So we can reconstruct every single implant that is placed on the actual location that the surgeon implants them. And then we can predict, in this case, have a quantitative comparison between choices from fibular grafts to tibial grafts to femoral grafts, and then tell the surgeon, hey, when you're loading this structure in this way, right, you're effectively exhibiting some sort of displacement on your spine. And that displacement is given by, 0.12 millimeters, 0.1 millimeters, or in the femur, in this case, is about 0.005. And this has a physical meaning, right? Because from, if I take you back to your physics classes, you're changing the inertia of your bones. You're changing the material distribution of your bone, and you're changing the angle orientation of the bone, so all those forces are being distributed differently between each one of those reconstructions. And then we can go in more deep and analyze implant positions, right? Why do we use 4 screws, not 3 or 2 in an optimal position? So we can take, what we know from structural analysis, screw analysis, and then adopt it here and have, the pretension that the surgeon imposes into the specific structure, and then analyze how the axial forces that prevent screw pullout will act on the specific reconstruction, and we can see that those 4 screws that are listed, some on the ischium, some of the tibia, will experience higher forces and lower forces because there's position dependency, right? You have some of them that will be in compression, some of them that will be in tension, balancing the structural load of your structure. And then we can go in and vary not just positions, but also materials, right? Because we have choices between titanium or stainless steel, which might be, structurally more sound, versus others, ones that are resorbable like magnesium or some other carbon fiber or polymer materials that might have lower stresses, but might promote osseointegration because the stress gradients across your structure are less. So how do we balance, having high structural integrity in your screws versus promoting perhaps higher or accelerated healing when you're balancing the stresses surrounding those areas, right? Because you want the bone to have the load, not just carrying by the implant. And then we also work sort of like in that space from, soft in the body to now the technologies themselves. So some of this is related to wireless neurotechnologies as well, where if you are ever in this space and trying to do some sort of wireless experiments, you have to care about electromagnetics, you have to care about efficiency, you have to care about some of these miniaturized mechanical electrical systems where you have wires, you have electric fields coming on, you have micro LEDs. So how do you enable these technologies from a mechanical perspective to combine fluidic interfaces, mechanical interfaces, chemical interfaces, all of them through modeling? Because, if you're an experimental group and you're going to spend all your budget, figuring out how to optimize the system, there's an opportunity to collaborate with us, and we tell you, hey, this is the scaling, this is the model that you need to be able to optimize your specific experiment, right? So we go from optogenetic devices, optofluidic devices, photofluidic devices, integrating electrochemical interfaces, mechanical interfaces, thermal interfaces to enable sensing and also delivery of drugs at programmable timescales. So we have, photofluidics technology here, integrating microchannels, drug reservoirs, flexible membranes, coil harvesting antennas, and then optical probes to record all the sort of delivery as it's happening in real time. And you can predict, not just the operation for multiple deliveries, but then also do the modeling here to understand spatially how the drug diffuses in this porous media, and then correlate what you're seeing in your simulations to what you're seeing in your optical probe recordings and have matchings of the flow rates, the drug, and then specific experiments that you might want to run. So all of these before you go in and do a bunch of design of experiments, have some simulation guided, experiments beforehand. So with that, this is my research group. We're open to collaborations. If you're ever finding yourself asking the question, how do we design, how do we model, how do we build X, Y, and Z in your lab, come talk to us, and we're happy to help you figure out how to answer that question.